Good morning to all. Myself Gopinath Sadhu, a PhD student at Department of Mathematics at Indian Institute of Technology, Guwahati, India. First of all, I want to thank the organizer uh, for giving me opportunity to present my work at this wonderful platform. Now, the title of my talk is The Effects of Heat Therapy Derived Inosine Generation on Tumor Reoccurrence. And these are my outline of this talk. First, I start with the background, then followed by the importance of inosine. Then I directly go to the problem statement. Then all the biological hypotheses, all these things are put into mathematical form, and these are taken care in this mathematical modeling section. Then and we simulated our model to get some results, and we discuss with about some result. Then we conclude what we find out from this study, and at the last I will show some useful reference which I used to conduct my study. So from this slide, we can see that in 2021, 18.1 million new cases were arises at global level, and almost half of it comes from Asia, 48.4%, and 23.4% from Europe, 21% from America, and 5.8% from Africa, and 1.4% from Oceania. So cancer is a global threat to socioeconomic, patients, family, and all those stuff. So to every cancer patients will go through certain treatment regime, and I have listed few of them here. So most common type of remedies are available in the treatment, and like surgery, radiation therapy, chemotherapy, immune therapy, hormonal therapy, targeted therapy, and stem cell therapy. This therapy can be used single or also combination therapy also available. But despite having all this such world-class has medical facility, cancer can reoccurrence again even after therapy. So now the question naturally comes to our mind, and how does cancer cell manage to reoccurs of a disease uh, again after therapy? Since our work is emphasized on how the heat and radiation therapy after the heat and radiation therapy cancer reoccurrence occurs, so most of literature where here we cited are in this aspect where the cancer is reoccurred after radiation and heat therapy. So clearly in this one's literature one, Kevin and campuses shows that radiation can be backfired, and they show that it helps to accelerate metastasis growth. And also Ismatabdi et al. Also decode how this reoccurrence mechanism is happening. And recently, Chen and et al. Experimentally shown that the inosine is secreted by dying and dead cell as a result of heat and radiation therapy, and this chemical is actually help to regeneration, tumor, and invasion. So based on this experimental performed by Chen and et al., we investigate inosines, the role of inosine secretion by dead cell through the heat and radiation therapy on tumor progression. So from this schematic diagram, we can see that a patient is undergoing a heat and radiation therapy. Before radiation therapy, tumor can be typically look like this type, where tumor is surrounded by healthy tissue. But when once the patient is undergone radiation and heat therapy, and basically this heat and radiation is directly projected on tumor surface, so naturally the cells are dying, but cells distribution can be heterogeneous, but here for sake of simplicity, we put it in at the center. Its dead cells are accumulated at centers. So our study emphasizes only that last aspect. All like already the patients is gone through the treatment protocol, and dead cell is already generated due to this therapy, and these dead cells are secreting the inosine chemical, and how this inosine chemical is impacting the tumor growth and regeneration again. So to formulate the mathematical model, we uh, we used the a well-known mathematical model is a proposed in 2006 by Chaplin and Lawless. So they investigated how tumor is tumor progression is happening, where they are encountered various things like tumor growth, their proliferation is encountered here, and invasion. The invasion is taken care by three component like chemotaxis, heptotaxis, also the random mortality they have considered, and they also consider UPA secretion, and this chemical or this chemical secretion is secreted by cancer cell. Also, they have considered the ECM remodeling. So to elucidate our problem, we extend this model into our work. So directly, if we go to the Chaplin and Lawless model, so they are given by equation 1, 2, and 3. In equation 1, and the cancer, how the cancer cell, they have used two compartment model, where cancer cell and the healthy part only they have considered the ECM only. So uh, how the cancer cell is diffused randomly, is taken care in equation 1 of right hand side first term, and how this UPA is involving the chemotaxis is taken in account in this second term, and how the ECM is involving in heptotaxis is taken care in this the third term, and also usual proliferation is also considered. And in ECM density equation, we can see that there is a degradation term, and degradation happening due to UPA, and also ECM is regenerated by this, and also UPA concentration and UPA we have they have considered the UPA diffusion, and also it is produced by tumor cell only, cancer cell only, and they have considered the natural decay. So just we extended their model by incorporating dead cell and the inosine, a concentration is inosine. So direct, if we go to our proposed model, so the red highlighted terms we are added here. So since treatment is already over, so we have directly considered dead cell is present and it is kept it fixed. So dead cell dynamics is not considered here. Just we consider dead cell is present, and these dead cells are occurred from the heat and radiation therapy. And if we look at that, the last term of equation 4, and this is the proliferation is due to the inosine. And a mass balance equation for inosine, and it is given by equation 6. So first two term is inosine production, and it is clearly there is an heaviside function. So in literature and Chen and et al, they seen that after certain time later inosine is generated. So this is also taken into our model, and this inosine is degrade here, and one kind of one we can say it's consumption by cancer cell, and this model is our proposed model. So to non-dimensionalized our model, we put we consider L is the characteristic length where the tissue domain is considered, and T is the diffusion time scale of any chemical in the tumor region. So based on this, we put it the non-dimensionalized form, and this is given by here, and we convert our dimensional equation to non-dimensional, and it is given in equation 11 to 8 to 12. And the corresponding to close our model, the corresponding initial and boundary condition are proposed. Here we consider the no flux boundary condition for both the spatial derivative are present for that equation, and it is given by equation 13 and 14. And the one of interesting thing is here in initial condition, we can see that in equation 15, a very tiny small amount of cancer cell we considered, and rest and dead material D is kept to be fixed here, and it is present in greater amount, and initially inosine concentration kept it 0. So to simulate our mathematical model, we use finite difference framework. For temporal derivative, we use finite difference, forward time difference, and for spatial derivative, we use central difference scheme. And we also ensure the robustness of our numerical method by using grid independency test. So, and these are the dimensionless parameters value we have used to conduct our simulation. And this is the qualitatively experimental matchup, and we can see that the it's have a good agreement with the experimental data and our proposed model. And also we have validated our mathematical model with Chaplin and Lawless. So also this picture shows me a great numerical validation with our model to existence work. And this picture defines the how the uh, inosine influence the cell proliferation, where diffusivity of cell is ignored here. Every diffusivity like chemotaxis, heptotaxis, and random mortality, all these things are ignored. Just we kept it as a ODE model, and we simulated here. So we can see that inosine have a after T is equal to 50, inosine is generated. So proliferation is much higher in this figure A. And figure B represent when for the various spatial location, how the cancer cell evolve with time. And it is given in figure B. Also, we have here we also include the diffusivity only for cancer cell. So, and the heptotaxis and chemotaxis process are ignored. So we can see that when diffusion is increases, so cancer cells are going towards the healthy domain, and also the temporal evolution of various location of tumor region, we can see that they are evolution here. And also we simulated our result when we put heptotaxis into the account where chemotaxis are ignored. So we can see that when heptotaxis is in the coefficient of heptotaxis is increases, so cancer cell are going to invade ECM more heavily. And this figure A and C are the spatial distribution of cancer cell and ECM are given in A and C respectively, and the temporal distribution of cancer cell at various location is given in equation B, and the UPA concentration also given in equation D. So also only chemotaxis are taken into account in this model. So we can see that when chemotaxis are coefficient are increases, so cancer cell are not invading the ECM region. So they are dominated at the central portion only. And these are this is given in figure A, and also time evolution of cancer cell at various location in given in figure B for various for the chemotaxis coefficient. And also we have taken both of them, like hepatotaxis, chemotaxis, all these things are put in here. So we can see that when only this chemotaxis coefficient and hepatotaxis coefficient are ignored, only diffusivity is present. So, and when all these things are present here, so we can say that there we can see that there is huge change in the cancer cell density at at the tumor site, and also their temporal distribution at various location also observed. And also we have see that there is decay, there is much decay of ECM. So there means when hepatotaxis and chemotaxis both are considered in comparison to when only diffusion considered, so cancer cell uh, more more invading to the surrounding. And this is the constant, this is the figure when UPA distribution are all are given for spatial and temporal also given in A and B, and for inosine concentration are also given in equation in C and D. So you can see that at when only diffusivity is there, so inosine have higher amount at the central part, and when is low, it is low when both chemotaxis and hepatotaxis are considered. And this is the temporal distribution of inosine and inosine for both the case when diffusivity only considered and the chemotaxis and hepatotaxis are considered. So from this study, we can outcome these things. It can be noticed that inosine is generated after some radiation treatment withdrawal, and it is achieved as an Gaussian profile. And inosine take maximum concentration at location where tissue domain where dead cell density is maximum and decreases in density. And cancer cell proliferate with usual proliferation, but when once the inosine gets generated from the dead cell, the proliferation intensity of cancer cell is much enhanced. And due to diffusion, cancer cell is spread through through and infect the surrounding healthy region. And due to ECM degradation via UPA, cancer cell migrate toward higher density of ACM. And the presence of inosine facilitate the tumor invasion via migrating cancer cell due to hepatotaxis and chemotaxis process. And at last, I want to acknowledge my institution, Indian Institute of Technology, Guwahati, to providing financial support to conduct this study. And also, I want to thank Dr. Kuldeep Singh Jadhav from Maulana Azad National Institute of Technology, Bhopal, Madhya Pradesh, India. We are both conducting this study, and these are the reference I used to conduct this study. And thank you for kind attention. And if you have any question, I will be happy to answer.